Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video in an entire list of videos on sequences and series. We have gone through sequence and summation notation. We talked about what a sequence is, recursively defined sequences, all that fun stuff, arithmetic, geometric sequences, their partial sums, the infinite sum of geometric sequences, mathematical induction and proofs by mathematical induction. And then we rounded it out with this set of videos about the binomial theorem. The beginning of this set of videos was about Pascal's triangle and how it relates to powers of binomials. And then we did what seemed to be an aside. We talked about factorials and then about combination notation, that n choose k. And the big question is, why go through all of that when we're supposed to be talking about, I guess, the binomial theorem? Well, it is because of this statement right here. Recall from the previous video the following values. 6 choose 0 is 1, 6 choose 1 is 6, 6 choose 2 is 15, 6 choose 3 was 20, and then due to symmetry, 6 choose 4 was 15, 6 choose 5 was 5, and 6 choose 6 is 1. Again, 1, 6, 15, 20, 15. Oops, there's something wrong with that. That should be a 6 right there. Once I was reading that out loud, I realized that's a problem. 1, 6, 15, 20, 15, 6, and 1. Now notice back here in our previous lecture on Pascal's triangle that those numbers are actually within Pascal's triangle. They are right here, 1, 6, 15, 20, 15, 6, and 1. So those coefficients in Pascal's triangle can be derived using the choose notation. In fact, it turns out, I'm just going to go ahead and write this actually on that page. And in fact, it's already written there, right? That 6 choose 0 is the 6th row of Pascal's triangle, and it's that 0th position. So in Pascal's triangle, remember I had mentioned it the first time, when you create Pascal's triangle, we're going to call this row the 0th row, and therefore this will be the first row. We're also going to call the first position in any given row. The first position we'll call the 0th position. So therefore this would be the first position, right? And that means that when we go to the 6th row of Pascal's triangle in the 0th position, the number should be 1. The 6th row in first position, the number should be 6, and so on and so forth. It's a wonderful way to build a binomial expansion without touching Pascal's triangle, if you wanted to do that. To be honest with you, I still build out Pascal's triangle, but this is a great tie between the binomial theorem, or those binomial coefficients, and Pascal's triangle, and binomial expansions, and the Fibonacci sequence, and chaos theory, and the golden ratio, and all the rest of the fun stuff. Fractals is what the word I was just looking for. So here is the binomial theorem in all of its glory, all of its splendor. A plus b to the nth power can be expanded out. Remember how I wrote this down when we were doing the Pascal's triangle video. A to the nth, and then start decreasing the powers all the way until you get a to the first, and then a to the 0th at the end. And then start with b to the 0th and work its powers up. B to the first, b to the second, all the way b to the n minus 1, then b to the nth. And then we had to use Pascal's triangle to figure out the coefficients. But now that we know the coefficients in Pascal's triangle are actually the same thing as this choose notation, Well, once I know the power, I'll use blue for that, then I can say, oh, take that power and choose 0 for the 0th position, then choose 1 for the first, 2 for the second, and so on and so forth down the line. By the way, those sub positions, these n choose 0, that's the power on B. N choose 1, it'd be B to the first, N choose 2 is B to the second, and so on and so forth. Now, I might just prove this, but I'll do it after some examples, because honestly, I'd like to get to examples before the proof. The examples that we're going to see are very common examples that you would see in a normal pre-calculus course. Find the term containing r to the 10th in the expansion of this binomial. First of all, I know that any given term of this binomial is going to look like the following. And I was going to write this out actually and have it pause the entire time, but I think it's better if I talk this through. So we know the coefficients from the previous theorem are the binomial coefficients, the choose notation. So I'm just going to go to the kth coefficient. Now remember, the way the binomial theorem is stated right here, your coefficients start at 0th. So you have the 0th coefficient, then you go to the first, the second, the third, and then so on and so forth down the line. And on top of that, whatever number we end with, that's going to be power on B, and the power on A is going to be n minus that number. So I'm doing this. I'm doing n choose k to kind of keep things arbitrary. So it should be a to the n minus k, b to the k. Again, k's will match here, and then that will just be n minus k because the sum of these two powers has to equal n. So we're going to go ahead and use that notation in the example that we're doing right here. So the standard term, any given term in this expansion, the kth term, if you will, looks like the following. N choose k, a to the n minus k times b to the k. Well, we know what a is here. A is this highlighted root 3, and b is the highlighted negative 2r squared. So let's go ahead and fill that in. This is n, choose k. We have a, root 3, raised to the n minus k. And we have b, which is negative 2r squared, raised to the k. What else do we know from this statement? Well, we know the power, actually. The power, which I'll just write in red here, is the 11th power. And so that's what n is. N is concrete, solid, anchored to be 11 for this entire problem. So let me go ahead and fill that in. 11, choose k. We have a root 3 to the 11 minus k. And then we have a negative 2r squared to the kth power. Great. Now we start asking, what do we need? What do we need? Well, we need r to have a power of 10 in the long run. So we need r to be to the 10th power. Well, if you take a look at this expansion or this random arbitrary kth term, it is 11 choose k. I'll keep that root 3 right there. Root 3 to the 11 minus k. But I could do this. I could write this as negative 2 to the kth power and r to the second to the kth power, or in other words, r to the 2k power. So I want 2k. I want 2k to equal 10. I want that power on r to be 10, so 2k has to equal 10, or in other words, k has to be 5. Great! Now I have everything I need. I just need to let in this term right here, this is an arbitrary term, now I know it's the 5th term, as long as we consider the very first term that we normally write down, if we consider that the 0th term. This is the 5th term. So let's go ahead and write that in. Thus, the term with r to the 10th is 11 choose 5, because that's what k is, root 3 to the 11 minus 5. Let's see what else we have. Negative 2 to the 5 and r to the 10th. Now, that is kind of bad if you leave it like that. So we're going to go ahead and see if a little bit of math can clean this up. But I'm going to tell you right now, these numbers are going to get large. This is very typical that the numbers get out of control with these because you're dealing with a high level of expansion. This is the 11th row of Pascal's triangle, so these numbers are somewhat large. But this will be equal to 11 factorial over 5 factorial times 11 minus 5 factorial. Let's see, I have root 3 to the 6th, or in other words, 3 to the 6 over 2, or 3 to the 3rd, right? Because obviously 11 minus 5 is 6, and 3 to the root 3 is 3 to the 1/2, so 1/2 of that 6 is 3. And then negative 2 to the 5th is negative 32, and then we have r to the 10th. From this point forward, it's actually not bad, but that 32 is just going to be miserable. But so is that 11, actually. It's 11 times 10 times 9. Once I see that these numbers are a little massive, 11, 10, 9, 8, 7, 6 factorial, I almost know I'm going to grab a calculator here. 5 times 4 times 3 times 2 times 1 times 27 times negative 32, and then r to the 10th. Most people would allow you to leave this in unsimplified form, but I'm just being 5 and 2 go into 10. I'm just going to be a stickler about this. 4 goes into 8 twice, 3 goes into 9 3 times. And you could see, now I'm just going to go ahead and grab a calculator because these numbers are massive. So let's go ahead and do that. And as I was just saying, you can see these numbers get pretty crazy. And so in a situation like this, let's say it was an exam or something like that, I would allow my students for something this large, I would just say in the exam, leave your number uncomputed. I just want to see that you can get to this point because these numbers are ridiculous. Unless I allow you calculators, which I'm not sure if I will, but I might actually on that next exam, who knows. If you're not in my class, just ignore everything I just mumbled. So that's how you would find a term in an expansion. But what else can you do with the binomial theorem other than just expanding a binomial and finding the term within a binomial? And now we arrive at kind of a bigger problem that a lot of people don't actually deal with when they're dealing with binomial expansions. It's very rare that somebody says, hey, factor this, and they expect you to recognize it's an expansion of a binomial. But this is actually the expansion of a binomial. I made a mistake earlier. That's why I had to scratch all that stuff out above. So how do I know this is an expansion of a binomial, and how would you know? Well, probably the first key or clue to this is the decreasing powers on y. Y to the 5th, then to the 4th, then to the 3rd, to the 2nd, and to the 1st. The second clue would be the increasing powers on z. Z to the 0th, Z to the 1st, 2nd, 3rd, 4th, and 5th. Let me use a different color highlighter like I meant to. There we go. 4th and 5th. So this looks to me to be the 5th power of a binomial. And I know it's the 5th power because the ultimate power in each of these terms is 5. So I'm going to go ahead and assume, even if it's wrong, I'm going to try to assume it initially, that this is some a plus b quantity to the 5th power. Now our goal here is to find out what a and b are. And it turns out that you can find the pattern to a binomial expansion just by looking at the first term of the expansion and the last term of the expansion, if it truly is a binomial expansion. How? Well, the very first term is it's technically the 0th term, right? So the 0th term is the power, choose 0, times a to the 5th, b to the 0th. So that 32y to the 5th is actually 5 choose 0, a to the 5th. That allows us to find a. Likewise, the last term is power, 5, choose power, 5, and times b to the 5th. So we know that 5 choose 5 times b to the 5th should be negative z to the 5th. But we also know that 5 choose 0 and 5 choose 5 are both 1. So those numbers, those coefficients, I can just erase. So now I know a to the 5th is the same thing as 32y to the 5th. That is, so let me write this, a to the 5th is equal to 32y to the 5th, or in other words, a is equal to 2y. And b to the 5th is equal to a negative, oops, that was supposed to be a negative, z to the 5th. Therefore, b is equal to a negative z. You raise both sides to the 5th, you will get a negative z to the 5th. And so I think that this polynomial is actually just 2y minus z raised to the 5th power. Now you might want to check that. In fact, I sincerely think you should. So to check that, just take any of the terms in there. Let's go for this guy right here. This is the second term in the expansion. I know it looks like the third, right? But the highlighted yellow piece is the 0th term. So that's the second term. So that term, if this binomial is correct, that term should be power choose 2 times a to the third b to the second. Remember that this 2, let me highlight that, should match the power on b. And the powers on a and b should add up to 5. That's how I knew it was a to the third, if you're wondering that part. So let's go ahead and test this out. 5 choose 2. 5 choose 2 is the same thing as 5 factorial over 2 factorial times 3 factorial. That'd be 5 times 4 over 2, or in other words, 10. So this is going to be 10 times a cubed is 2y cubed. B squared is a negative z squared. Let's see, 3 cubed is 8 times 10 is 80. Y cubed z squared, is that what it is? Yes, it is. Absolutely. So I feel very confident that this is actually the binomial that this polynomial factors into. Again, that's a very tough one just because it's hard to see that this can factor. But if you can factor things down, this is a really cool way to do it. Finally, I love patterns. If you watched the first video in this series on binomial theorem, you know the link between Pascal's triangle and the Fibonacci sequence. However, there are so many other cool things hiding in the background when it comes to this material. For example, find the sum of each row in Pascal's triangle. What do you notice? All right, let's go ahead and go back to Pascal's triangle. Be right back. Here I am, I'm back. All right, so let's go ahead and find the sum of each row this time. And if you watch my previous video, we found the sums of the diagonals when you slid things over to the left. But now I'm really asking about just find the sum of each row. So I'm going to write this in, let's use blue. So this row, if you add it up, is 1. This row, if you add it up, is 2. This row, if you add it up, is 4. This row, so the 0th row sum to 1. Second row, or first row sums to 2. Second row sums to 4. Third row sums to 8. That's the third row. Fourth row, let's see, that's 10, 14, 15, 16. I hope you see the pattern. Fifth row, you could probably guess is going to be 32, which is 2 to the 5th. This is 2 to the 4th. This is 2 to the 3rd. This is 2 squared. This is 2 to the 1st. And this is 2 to the 0th. So the ith row of Pascal's triangle, considering that the top row is called the 0th row, the ith row sums to 2 to the ith power. That looks to be true. Let's go ahead and prove it. So again, this is the nth row. This, we think, should sum to 2 to the nth power. And now we're asked to prove it. Now, to be honest with you, when I went to go prove this the first time, I was trying to prove this using mathematical induction. And you can, it just takes a long time and a lot of justification. But it turns out that this actually can be done much easier with noticing that these are the coefficients of an expansion. Of a binomial expansion specifically. So I'm going to claim right now that the binomial 1 plus 1 raised to the nth power is just that binomial expansion, which it is, honestly. So this is playing the role of A, and this is playing the role of B. Well, then 1 plus 1 to the nth is equal to n choose 0, the 0th term, a to the nth, b to the 0th, plus n choose 1, a to the n minus 1, b to the 1st, plus, and then you can continue down the line until you get to n choose n minus 1, which will be a to the 1st, b to the n minus 1st, and finally, plus n choose n, b to the nth. However, a and b are both 1. So let a equal b equal 1, and we get the result. And this is much, much easier than using proof by mathematical induction. If you let a and b equal 1, you get the summation right here. Now, what does this mean? It means that 1 plus 1 to the nth, which is 2 to the nth, is equal to that sum. We're done. We've proved it. The sum of the nth row of Pascal's triangle is 2 to the nth. It was a very easy proof. Very elusive, though, because a lot of people won't think of this summation right here, myself included, as the sum of a binomial expansion, but it is. It's just 1 plus 1 to the nth. Very, very interesting way of proving this, but there you go. Very, very cool property. And I think that this is a good point to stop this video. I'm not going to go back and prove the binomial theorem. That is in most standard textbooks, and it's a proof by mathematical induction. It's good to read those. All right, I hope you have a wonderful day, and I hope this helps you out.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.